In this lecture, we're going to discuss how a metal alloy is classified and what are their common applications. And then we're going to learn what heat treatment procedures are used to improve the mechanical properties of steel. Metal alloys, by virtue of composition, are often grouped into two classes, ferrous and non-ferrous. Ferrous alloys are those in which iron is the principal constituent. And we can further classify ferrous alloy into steel and cast irons. They are classified by this composition point from the iron-carbon phase diagram, where it's the composition of 2.11 weight% of carbon, which is the maximum solubility of carbon in austenite. So if the carbon content is less than 2.1 weight%, then it's steel. When the carbon content is greater than 2.1 weight%, then it's considered as cast irons. So in general, we say that a steel is an alloy of iron and carbon and other alloy elements that is capable of being hot or cold deformed into various shapes. Whereas for cast iron, because it has more carbon, which means it will be more brittle and harder. So we can say a cast iron is an alloy of iron and carbon and other elements, and it's not normally capable of being hot or cold deformed. So no matter we have steel or cast iron, the microstructure includes ferrite and cementite. And also, even though we say the cast iron in general is steel or is a ferrous alloy, has a carbon content of greater than 2.1 weight%, but in practice, most cast irons contain between 3.0 and 4.5 weight% of carbon. Now we understand that ferrous alloys are iron-based alloys, which can be further classified into steels and cast irons based on their carbon content. It is also important for us to understand the nomenclature for steels based on different standards. The most commonly used standards are AISI, which stands for American Iron and Steel Institute, and SAE, which stands for Society of Automotive Engineers standards. So the AISI SAE designation for these steels is a 4-digit number. The first two digits indicate the alloy content. The last two digits give the carbon concentration. For example, plain carbon steels starts with 10. So the first two digits, 1 and 0, indicate it is a plain carbon steel without any alloying element. And so far, so on. There are other examples, for example. And the last two digits, again, indicates the weight% carbon multiplied by 100. For example, if we have 1060 steel, 10 means it's a plain carbon steel. 60 is the weight% of carbon multiplied by 100. Therefore, 1060 steel is a plain carbon steel with 0.6 weight% of carbon. For information, steels can be further classified into low alloy steel and high alloy steel. And for low alloy steels, we can further divide it into low carbon steel, medium carbon steel, and high carbon steel. And they have different resultant properties because of the carbon content and the different alloy elements, so they can be used in different applications. So from low carbon to high carbon steel, it has increasing strength, cost, but decreasing ductility. Steels and other ferrous alloys are consumed in exceedingly large quantities because they have such a wide range of mechanical properties, may be fabricated with relative ease, and are economical to produce. However, they have some distinct limitations, including 1. A relative high density, 2. Low electrical conductivity, and 3. Susceptibility to corrosion in some common environments. So thus for many applications it is advantageous or even necessary to use other alloys that have more suitable property combinations. And here we're going to presenting several commonly used non-ferrous alloys. And alloy systems are classified either according to the base metal or according to some specific characteristic that a group of alloys share. So the first one, copper alloys, which includes brass, bronze, and copper beryllium alloy. And then titanium alloys, it has relatively low density and reactive at high temperatures, so they are used in space applications. Aluminum alloys has a low density as well. We can have other alloy additions into aluminum to form solid solution or precipitation strengthening, and those aluminum alloys are used in aircraft parts and packaging. Magnesium alloys, again, has very low density, and it is used in aircraft and missiles. Refractory metals has very high melting temperatures, can be used in high temperature applications. And noble metals, they are oxidation and corrosion resistance. Oftentimes, we need to achieve the desired properties of the material. The use of heat treatment on commercial alloys is an exceedingly common practice to alter the properties of the material. So, let's talk about heat treatment. So heat treatment is defined as the controlled heating and cooling of metals for the primary purpose of altering their properties, which includes strength, ductility, hardness, toughness, and machinability. Heat treatment can be done for strengthening purpose. For example, converting the microstructure from austenite to martensite, which is hard but brittle. Heat treatment can also be done for softening and conditioning purpose, for example, annealing or tempering to restore the ductility of the material. Almost all of the heat treatments of steels are directed toward producing the mixture of ferrite and cementite that gives the proper combination of properties. So which means we want to formulate a microstructure that consists of the right mixture of metal-like faces that are tough and ceramic-like faces that are hard and brittle. So we will limit our discussion of heat treatments to the heat treatments for steel only, and also we will only focus on several simple heat treatments, including stress relief annealing, which is used to eliminate residual stress after hot work. Full annealing, which is also called coarse grain annealing, which means to increase the grain size so as to improve the machinability. Normalizing, which is used to refine grains and creates a more uniform and desirable size distribution. The result will be tougher steel. And then quenching plus tempering. So quenching is followed by tempering to achieve a hard and wear resistance surface or to increase the strength of a workpiece. So for annealing and normalizing, all of those processes, the driving force is to achieve a lower energy state. In other words, is to maintain or is to reach a thermodynamic equilibrium, because at equilibrium state, the energy is the low energy state, is the lowest state actually. Whereas for quenching and tempering, the principle leads to thermodynamic imbalance state of the microstructure due to rapid cooling. So they have a distinctive difference between the principle of annealing, normalizing, and quenching, tempering. In order to influence the hardness and the strength of a steel, a special heat treatment, which is called quenching, followed by tempering, has been developed. The quenching and tempering process can be divided into 3 basic steps. The first step is austenizing, which is to heat above the GSK line into the austenite region. In other words, we want to form austenite. That's the first step, is to form austenite. So that GSK line is this line. G is the point on the top, and then this is the G and S and K. Okay, so about this line we will form austenite. And the second step is quenching, which means rapid cooling up below the austenite pearlite transformation. And tempering is reheating to moderate temperatures with slow cooling. Depending on whether a high hardness or a high strength has to be achieved, the final process, the so-called tempering, is carried out at different temperatures. When a steel has to become very hard, it is only tempered at relatively low temperatures, while it becomes tougher and high load capacity at higher temperatures. So, if the tempering is at a low temperature and the result is high hardness, the process is called hardening process. Whereas if the tempering is carried at a high temperature and resulted in a high strength and toughness, then the process is strengthening process. So now we can visualize these 3 steps for quenching and tempering, which is plotted in this time temperature plot. Austenizing, heating to above the GSK line into the austenite region. Quenching, a rapid cooling to below gamma alpha transformation. And tempering can happen at 2 different temperatures. At lower temperature, between 200 degrees Celsius to 400 degrees Celsius, the resultant material is harder but more brittle. So this process, tempering process, is hardening process. Or the tempering can be at a higher temperature, between 550 to 7 degrees Celsius. So now this process again, the quenching, is not cooled down slowly but relatively quickly. So that's why it's called quenching. In the first process step, the steel is heated above the GSK line. This completely transforms the BCC or body-centered cubic lattice structure of ferrite to the FCC structured austenite. So austenite has FCC structure and ferrite has BCC structure. Now, if the steel were to cool slowly again in this state, the austenite lattice would be transformed back into the ferrite structure, which is almost insoluble for the carbon. Due to the relatively slow cooling, the carbon atoms would have enough time to diffuse from the transforming austenite lattice and form again the intermediate iron carbide compound, or the cementite. So thus, a slow cooling from the austenite state would only restore the initial state of the microstructure, and the desired structural change would therefore not occur. Instead, it must be cooled relatively quickly to achieve this BCT structure of the martensite. So this represents the next process step, which will be explained in the next slide. If the austenized steel is not cooled slowly but quickly, the dissolved carbon no longer has enough time to diffuse out of the austenite lattice. Such rapid cooling is called quenching. Quenching is the rapid cooling of a material from the heated state. So during quenching, the carbon remains forcibly dissolved in the forming ferrite lattice despite the transformation of the lattice. So the body-centered cubic elementary cells of the ferrite structure are expanded tetragonally by the carbon atoms forcibly dissolved therein. So this tetragonally widened lattice structure is a new type of microstructure, which is called the martensite. So the formation of the martensite microstructure can no longer be explained by the iron-carbon phase diagram, because that is an equilibrium phase diagram. So this structure is an imbalanced structure, or doesn't exist under equilibrium conditions. And that is why the TTT diagram, the time temperature transformation diagram, is used. The reason why the martensite is hard and brittle is first because the lattice distortion of the martensite structure leads to an extremely strong obstruction of the dislocation movement. And secondly, the pure martensite has no slip planes and therefore cannot be plastically deformed. So the martensite microstructure formed after quenching is characterized by a very high hardness, but is much too brittle for most applications. So in order to give the quenched steel the toughness required for use, the microstructure must be treated again afterwards, and this is done by subsequent tempering. Tempering is the reheating of quenched steel to reduce brittleness and to increase toughness. So this is due to the increased temperatures during tempering. The forcibly dissolved carbon atoms in the tetragonal martensite can partially diffuse out again. Accordingly, with the decline of the tetragonal martensite, the lattice distortion partially decreases, and this reduces the hardness and strength slightly, but the steel gains significantly in toughness. Even if the hardness and the strength values have decreased more or less after tempering, they are still significantly higher compared to the original microstructure before quenching. And after tempering, steel is generally cooled slowly in air. Depending on the temperature and the tempering time, the property values such as hardness, strength, and toughness can be specifically controlled. The necessary temperatures for certain property values can be read from corresponding tempering diagrams. So this is one tempering diagram, which is a plot of ductility in terms of elongation or percentage of elongation, yield strength, and tensile strength as a function of tempering temperature. So in principle, the higher the tempering temperature and the longer the tempering time, the greater the increase in toughness. So toughness is a combination of strength and ductility. So it has to be strong as well as ductile for the material to be tough. However, the hardness value decreases again accordingly. So if the steel is to be very hard and wear resistance, a high degree of hardness is essential. Then the steel is tempered accordingly at relatively low temperature, and this process is referred to as hardening, and the steel is called hardened steel. And if, on the other hand, the focus is on achieving high strength with high toughness, the tempering temperature are selected accordingly higher, and this process is then just called quenching and tempering or strengthening. So when tempering at low temperatures, the steel remains a relatively high hardness, and the steel is referred to as hardened steel. On the other hand, it's just called tempering and quenching. And tempering at relatively high temperatures leads to increased toughness with still increased strength. Now let's move on to other types of heat treatment for steel. The first one is stress relief annealing, which is used to eliminate residual stresses. So what are residual stresses? Well, if a steel is heated or cooled unevenly, then there will be internal stresses. And this internal stresses also known or is called residual stresses. So if a material has residual stresses, first of all, the strength of the material will be reduced. And second, during a subsequent machining process, the residual stresses can lead to distortion of the workpiece if they are suddenly released as a result. Therefore, we have to eliminate the residual stress, and the aim of stress relieving annealing, by the name, is to release residual stresses. The stress relief annealing is done at about 80 to 170 degrees Celsius below the eutectoid temperature, which is this A1 line on this time temperature diagram. So the material or the specimen will be placed into a furnace at the controlled temperature. Again, it's about 80 to 170 degrees Celsius below the eutectoid temperature. And after annealing, after a period of time, the workpiece must then be cooled down to avoid a renewed occurrence of stress. And in most cases, the workpiece remains stationarily in the switched off annealing furnace to be cooled down naturally. The other two forms of annealing for ferrous alloys are full annealing and normalizing. Of course, there are other types of annealings for steels and other alloys as well, but we will only focus on those two, full annealing and normalizing. So from this temperature composition or phase diagram, we can see the normalizing is at this temperature region, colored in pink, and then full annealing happens at the temperature zone colored in blue. So full annealing is also called coarse grain annealing, which will result in bigger grain sizes, and the result will be improved machinability or ductility. Whereas normalizing will result in refined grain size or smaller grain size. And it also creates a more uniform and desirable size distributions. And the result will be tougher steel. Well, for full annealing, it can be considered as one method for dispersion strengthening. Well, we mentioned dispersion strengthening versus solid solution strengthening. So for solid solution strengthening, we just have one phase. And for dispersion strengthening, we'll have at least two phases in the material. And the overall property is better than with just one phase. So steels can be dispersion strengthened by controlling the fineness of pearlite. Since, for example, for hypoeutectoid steel, the microstructure or microconstituent at room temperature will be proeutectoid alpha or ferrite plus pearlite. So with full annealing process, we can control the size of the pearlite and in turn control the mechanical properties of the material. So here is the process for full annealing for hypoeutectoid and hypereutectoid steel. So the trend is very similar. It's just that the temperature we're gonna heat up to is different for hypo and hypereutectoid steel because of if you check the iron carbon phase diagram, the temperature will be a little bit different. So there are two steps for full annealing. First step is the steel is initially heated to 30 degrees above the A3 temperature, which is the boundary between the alpha and the gamma phase, and hold in the furnace for long enough to produce homogeneous austenite. And then cool the steel down slowly in a furnace, again in the furnace, and which will produce coarse pearlites, and the resultant mechanical property will be ductility material. Normalizing is also related to dispersion strengthening, and the procedure or process is also very similar to annealing or full annealing. It's just that the temperature is a little bit higher than the full annealing temperature. So the steel is initially heated to 55 degrees Celsius above this A3 temperature, and again hold in the furnace for long enough to produce homogeneous austenite. And the step 2, instead of cool it slowly, it will be cooled down fast or rapid cool in air, which will produce fine pearlite, and the resultant property will be tougher steel.